Hello students, welcome to the course Physics Principles and Applications for FY BSc Physics Paper 2 Semester 1. I am Dr. Amol Rahane, welcomes you to today's lecture. In the previous lecture, we have studied the rotational energy levels of a diatomic molecule. In this lecture, we are going to study the vibrational energy levels of a diatomic molecule. So, we are studying the third chapter, Physics of Molecules. So, let us study today's topic, vibrational energy levels of a diatomic molecule. So, we know that when two atoms combine to form a stable molecule, for example, HCl or carbon monoxide, they may be said to do because of some internal electronic rearrangement. It is because the whatever molecule we are saying it is formed when two atoms they come closer, then there will be some rearrangement of electronic structure of these two atoms when the molecule is formed. So there are several interactions between the ion and electrons in the two atoms. So we know that the two ions, they are positively charged ions, right, or ion cores. These two positively charged ion cores, they will repel each other, right. So there will be repulsion between the positively charged ion cores. Also there will be repulsion between the negatively charged electrons of the two atoms, right. That means the repulsion will be there between the positively charged two ions as well as negatively charged electrons of the two atoms, both the atoms. So this is one case. We will also have an attraction between the positively charged ion of one atom and the negatively charged electron of the other atom, and vice versa. That means in addition to the repulsion, we will also have an attraction between oppositely charges. So positively charged ions and negatively charged electrons of the other atom. So there are these two terms, we can say the attraction term and repulsion term, and these two terms they will balance at a point where the bond is formed, right. So we can say the two atoms settle at a equilibrium interatomic distance. So they will settle at an equilibrium interatomic distance, and we call this interatomic distance R equilibrium, right. So where R equilibrium is the distance at which two atoms settle at that point, and where the repulsive force and attractive force between the two atoms they will balance each other, and therefore we get the stable molecule, right. So we can say at this point the potential energy of the molecule will be minimum, right, and therefore we can say the potential energy of the molecule will be minimum, right. So let us see the diagram. So here our two atoms, we are saying they are at the infinity, and therefore their potential energy is also close to 0, right, at infinity. So they are at infinite separation from each other, and therefore their potential energy is also close to 0. But when they will approach each other from infinity, they come closer, their potential energy start decreasing, right, and at a certain point where the bond is formed, their potential energy will be minimum, right, and that particular separation between the two atoms we call it the equilibrium separation or bond length, where the bond is formed. If we further try to squeeze the two atoms, right, we further try to push the two atoms closer, then the repulsive term become dominant over the attractive term, right. The repulsive term become dominant over the attractive term, and these two, we can say the potential energy of the molecule will increase, right. So the potential energy of the molecule will increase if we further try to reduce the bond distance, right? And therefore we can say the potential energy varies in between this region, right? So if we sufficiently excite the molecule, then we can say the molecule will try to vibrate, right? So molecule will try to vibrate about its mean position, and therefore its potential energy also change, right? So it will change about the interatomic separation, right? And this we have plotted here. Now let us consider a polar diatomic molecule like HCl. So we are considering a polar diatomic molecule. A polar molecule means which is formed due to molecules of atoms of different elements, right? The polar diatomic molecule means the molecule which is formed by the atoms of different elements, and therefore there will be when the covalent bond is formed between these two atoms, in that case one of the atom will have more electronegativity than the other. Let us take an example of HCl. So in HCl what we have is chlorine is more electronegative than hydrogen, and because of that chlorine pulls the electron pair towards itself, and therefore we can say the chlorine becomes slightly negative and hydrogen becomes slightly positive, and because of that we can say the HCl molecule it becomes polar, right? So this is HCl molecule. This is one of the example of polar molecule, right? So HCl. So let us consider a polar diatomic molecule like HCl, and we consider that okay, let us fix, this is chlorine atom and this is hydrogen atom. Let us say, let us fix or anchor the chlorine atom at one axis, right? So let us anchor it at one axis and imagine pushing and pulling of the H atom closer or away from the Cl atom, and we are considering okay, this hydrogen atom is coming near to the chlorine atom and it is going away from the chlorine atom, and this will change the potential energy of the molecule, right? And we have plotted the variation of the potential energy of the molecule against the atomic distance r that we have already seen in the diagram, right? So the minimum of the energy corresponds to the equilibrium distance r equilibrium, right? And near the minimum of the curve which corresponds to the stable configuration of the molecule, the shape of the curve is very nearly a parabola, right? So let us consider our molecule is vibrating about the mean position, we can say, right? So this is the potential energy. So potential energy is minimum at r equilibrium, and we consider that molecule is continuously vibrating about this equilibrium separation, right? So molecule is vibrating, and we can say the shape of the curve is parabola, right, here near the equilibrium separation. So the minimum of the energy corresponding to the equilibrium distance r equilibrium, right? So we will have minimum corresponding to the equilibrium distance r equilibrium, and near the minimum of the curve which corresponds to the stable configuration of the molecule, the shape of the curve is very nearly a parabola. We can let us say draw a parabola, so which is shown by a dotted line, right? So near the equilibrium separation, if the molecule is vibrating, and we are saying the shape of the molecule is of parabola. So we are approximating our diatomic molecule to this small region, and we are saying that okay, the potential energy is following a parabolic path, right, within that short region, right? Now the vibrating diatomic molecule may be considered to be equivalent to the two masses connected by a spring, right? So if M1 and M2 are the masses of the two atoms of the molecule, then the reduced mass of the molecule is, right? So reduced mass mu is equal to M1 into M2 upon M1 plus M2. So mu is the reduced mass of the molecule. The vibrations of the spring may be unharmonic, right? The spring may be vibrating unharmonically, right? So we are approximating the vibrating diatomic molecule. We are saying that it undergoes small vibrations only, right? And so that it follows the simple harmonic oscillations. So we know that simple harmonic oscillations, that means the periodic oscillations, right, about the mean position, right? So there is some restoring force. That restoring force balances this, we can say, the vibrations, whatever force is applied to that oscillator, right? So we have the periodic oscillations about the mean position or from the equilibrium distance, right? And therefore we are saying that our molecule, or we are saying that spring which follows the simple harmonic oscillations, right? So let us consider the spring obeys the Hooke's law, right? So restoring force which is directly proportional to the displacement from the mean position, right? So since it is the it obeys the Hooke's law, and therefore we are saying it is following the simple harmonic oscillations. So that means simple harmonic oscillator means the restoring force is directly proportional to the displacement from the mean position, and therefore that restoring force is given by F is equal to minus K into R minus R equilibrium, right? So where K is the force constant and R equilibrium is the equilibrium separation, right? And F is the force, right? And R is the we can say their separation between the two atoms, right? So in this case the energy curve is parabolic. So we have already seen that within that small region we have the parabolic curve, and we are approximating our diatomic molecule to this small region, and we are saying it is a parabolic approximation, right? And therefore the potential energy has a form, right? So the potential energy is given by V is equal to 1 upon 2 K into R minus R equilibrium square, right? So we can easily calculate this potential from the force, right? So we know that force is the negative gradient of potential, right? So if we take the integration of the force, we can easily calculate the this potential term. Now the classical frequency of oscillations of the diatomic molecule is given by nu is equal to 1 upon 2 pi root K upon mu, right? So we know that it is following the simple harmonic oscillations, and simple harmonic oscillator, we know that it has the frequency, and that frequency is given by mu is equal to 1 upon 2 pi root K upon mu, right? So this is the classical frequency of oscillations. So till now we have seen the classical picture or classical physics, what tells us that, right, about the simple harmonic oscillator. But when we consider a diatomic molecule, we are considering very small distances of the order of few angstrom, right? So we know that the bond length of the diatomic molecule is of the order of 2 to 3 angstrom, and we know that 1 angstrom is 10 raised to minus 10 meter, right? So we are considering very small distances of the order of 10 raised to minus 10 meter, and at this small size the we can say the classical physics fails to apply, right? And where the quantum mechanics emerge, and we have to apply the quantum laws at the very small distances, right? So we have the quantum physics. So we have to solve this simple harmonic oscillator problem quantum mechanically, and therefore we can say the vibrational energy of the molecule are quantized, right? And the allowed vibrational energies of the simple harmonic oscillator are given by the solving the simple harmonic oscillator problem quantum mechanically. So we have to solve the problem quantum mechanically, and the quantum mechanics tells us that the vibrational energies of the molecule are quantized. So what is meant by quantized? So quantization means that our energies, they are taking discrete values, right? So they are taking discrete values, just like in atom in the very first chapter we have studied in an atom, what we have, the atom has discrete energy levels, right? They have separate energy levels, and it cannot take arbitrary energy levels, right? So from the Bohr's principle we know that the that atom cannot take continuous energy levels, but energy levels of the atom are discrete, right? So similarly, the vibrational energies of the molecule, they are also quantized. That means the vibrational energies takes discrete values, and they are not continuous energy levels, right? And therefore we can write En is equal to En plus 1 half, so into bracket and into h nu, right? So that means this expression gives us the vibrational energies of the molecule, and we can say the vibrational energies of the molecule are quantized, because n is the quantum number and that takes values 0, 1, 2, 3 dash 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 up to infinity, right? So it is a vibrational quantum number, right? And this h, we know it is Planck's constant, and nu is the frequency of the radiation that is absorbed or emitted by the our molecule, right, during the vibrations, right? So quantum mechanically we get the vibrational energies of the molecule, and we are saying they are quantized. That means they are taking discrete values, right? By putting different values of n, we get different values of energy, right? So for n is equal to 0, we get En is E0 is equal to 1 half h nu. For n is equal to 1, we get 1 plus 1 half, so 3/2 h nu, right? We will see that in this figure, right? So the lowest energy state is for n is equal to 0, and it is called as the 0 point energy. So we have already seen that by putting n is equal to 0, we are getting energy E0 is equal to 1 of h nu. That means the lowest energy is not 0, right? So the lowest energy is non-zero, right? So please remember, the lowest energy of harmonic oscillator is non-zero, but it is 1 half h nu, right? And therefore we are taking this energy as a reference, and we call it 0 point energy, right? It is a reference energy, it is the lowest energy, and we are taking it as a reference. So our reference is, we are saying it is 0 point energy, even though it is not 0, but we are taking it as a reference, right? From here only we are taking all the energy levels, so we call it 0 point energy. The next energies are given by E1 is equal to 3/2 h nu. So we know that by putting n is equal to 1, we get E1 is equal to 3/2 h nu. By putting n is equal to 2, we get E2 is equal to 5/2 h nu, and by putting n is equal to 3, we get 7/2 h nu, and so on, right? So we will get different energies by energy levels by putting the value of vibrational quantum numbers. And again we can say the successive energy levels are equally spaced and are separated by h nu. So if we subtract E2 minus E1, so we will get h nu, right? Again if we subtract E3 minus E2, so we will get h nu. Again if we subtract E1 minus E0, we will get h nu. That means the successive energy levels, they are equally spaced and are separated by h nu, that we will see in the from this diagram. So we know the vibrational energies which are given by this formula, where n is the quantum number, vibrational quantum number, and which takes the values n is equal to 0, 1, 2, 3 up to infinity, right? For n is equal to 0, we get E0 is equal to 0 plus half h nu, which is equal to 1 half h nu, and that value, if I plot that value, if I show in the energy level diagram, so we will get for n is equal to 0, our energy is not 0, so it is En is not 0, but it is half h nu, and therefore we call it 0 point energy. For n is equal to 1, we get E1 is equal to 1 plus half h nu, which is equal to 3/2 h nu, and therefore we can plot this value here. For n is equal to 1, we get 3/2 h nu, and for n is equal to 2, we get E2 is equal to 5/2 h nu, and we can plot it here. For n is equal to 3, we get 7 by 2 h nu, and we can plot it here, right? Similarly, we can plot for n is equal to 4, we get 9 by 2 h nu, and n is equal to 5, we get 11 by 2 h nu, and so on, right? One can easily plot the upper energies, right? And if we see the separation between the two energies, so that separation is of the order of h nu, right? So all these separations, they are h nu, right? So all the energy levels, they are equally spaced in the vibrational energy levels, but in the case of rotational energy levels, they were not equally spaced, that we know, right? So here the energy levels, they are equally spaced, right? So these are the vibrational energy levels of a diatomic molecule, right? Now let us consider the vibrational spectrum of the diatomic molecule, right? So when the transition from higher energy state to lower energy state takes place, the energy is emitted in the form of radiation, right? But when a transition from lower energy state to higher energy state takes place, the energy is absorbed. That we know that from Bohr's principle, that from atom, when the atom jumps from lower energy level to higher energy level, in that case it will absorb energy, and when the atom jumps from the higher energy level to lower energy level, it will release the energy. So similarly here, in the case of molecule, the vibration, when the vibrating molecule jumps from one energy level to another energy level, it will either emit or absorb energy, and that is depend whether the atom is jumping from higher energy level to lower energy level. In that case, the atom will emit radiation, and when the atom jumps from lower energy level to higher energy level, in that case it will absorb the radiation, right? And there are some selection rules for the transition, right? So what are the selection rules? The selection rules for the transition between the vibration levels is shows that it states that delta n is equal to plus or minus 1, right? That means the vibrational quantum number should not change more than 1. When the atom jumps from one energy level to another energy level, the vibrational quantum number should not change by 1, right? More than 1. So it may be either minus 1 or plus 1, that depend on the whether it is absorption or emission, right? So only those energy levels are allowed for which the vibrational quantum number is changing by plus or minus 1, and all the other transitions are not are forbidden, right? All the other transitions are forbidden, right? They are not allowed. That means only the successive energy levels transition is allowed. That means transition from E0 to E1 is allowed, E1 to E0 is allowed, E1 to E2 is allowed, but not E0 to E2 or E2 to E4 is not allowed, right? Only the successive values, successive energy levels transition is allowed, where the quantum number is changing by 1 only, right? Plus or minus 1 only, we can say. And therefore the transition between any two successive energy levels will give energy is equal to h nu, that we have seen in the diagram. We will again see here, right? The frequency nu of the emitted or absorbed radiation is given by h nu is equal to En1 minus En2, right? So h nu is the energy, right, and which is equal to the difference between two energy levels, and therefore we get frequency nu is equal to En1 minus En2 upon h, right? And that frequency will be in hertz. That means from two energy levels we can easily calculate the frequency nu, right? And but we express usually when we calculate the spectrum, we express these fractal notations in per centimeter unit, and there what we use the wave number, right? So instead of getting the frequencies, what we get wave numbers, a transition at different wave numbers, the spectral lines at different wave numbers, and therefore we can convert that frequency into a wave number format, right? So we get nu bar is equal to 1 upon lambda. So lambda is the wavelength, which is equal to nu upon c, which is equal to En1 minus En2 upon hc, right? So which is in per centimeter, where c is the velocity of light, which is also is expressed in terms of centimeter per second unit, right? So all the successive transitions give the same frequency of emission or absorption. So that means transition between any energy levels, right? So we are saying n is changing, but here there is no n here in the case of wave number or frequency. That means all the transitions, they are giving the same frequency and single frequency, or they are giving the same or single wave number, and therefore they are giving the same wavelength, we can say. That means any transition between any successive energy levels, vibrational energy levels, that gives rise to the same frequency or same wavelength or same wave number, we can say. That we will see from this diagram, right? So here are the vibrational energy levels of the diatomic molecule, and this is, we know the energy expression, the difference between two energy levels, that is in the form of h nu, right? So nu is the frequency, and that is given by this expression. So we, in the wave number format, we get nu bar is equal to En1 minus En2 upon Sc, right? We express the spectral terms in terms of wave number, and therefore if I say the this energy, let us say the transition between n is equal to 1 to n is equal to 0 takes place. So in that case we get E1 minus E0 is equal to 3 by 2 h nu minus half h nu. So 3 by 2 h nu minus half h nu, which is equal to h nu, right? So that transition is here, right? So which is equal to h nu. For E2 to E1 transition, again we have 5 by 2 h nu minus 3 by 2 h nu, which is equal to again h nu, right? So that is shown here. Again, if we take the n is equal to 3 to n is equal to 2 transition, so E3 minus E2 is equal to 7 by 2 h nu minus 5 by 2 h nu, which is equal to h nu, and that transition is shown here, right? So similarly we can get all the transitions, right? So all the transitions here, they are giving the same frequency or same energy, right? So all the transitions, they are giving the same frequency. So when the spectrum is plotted, on the spectral spectrum is plotted, we will get the only single transition, right? So instead of getting several different transitions, we are getting the same frequency. So we are getting single frequency or single wavelength or single wave number, and therefore we will get single transition on the spectrum, right? So this is the vibrational energy levels of a diatomic molecule, right? So in the case of rotational energy levels or rotational spectrum, what we have seen, we have different lines, equally spaced lines for the rotational spectrum. But however, in the case of vibrational energy levels, what we have, only single line in the vibrational spectrum. So this is the difference between the rotational and vibrational spectrum of a diatomic molecule, right? For large oscillations, so up to here we have considered the we can say our molecule is following the simple harmonic oscillations. That means our molecule we are saying following very small oscillations, and within the region near to the equilibrium separation, we are saying it is following the parabolic approximation. That means our energy is parabola, right? But that means it is obeying the Hooke's law. But for the large oscillations, if the molecule is vibrating very largely, in that case it may not obey the Hooke's law, and therefore in the case of real molecules also, the bond length may not be elastic. The bond between the molecule may not be elastic. So sometimes the bond may break, right? When the large oscillations occur, the bond between the two molecules may break, and therefore we can say it is not elastic, right? And therefore for large molecular vibrations, they are unharmonic, right? They are not following simple harmonic oscillations, but they are unharmonic, and therefore as a result the spacing between the adjacent energy levels in for high n is less than the spacing between the adjacent levels of the low n. So that means what we have considered, the vibrational energy levels, they are equally spaced and their difference is h nu, right? Within the parabolic approximation, right? Within the simple harmonic approximation, we are saying our molecule is having very small vibrations, and because of that bond length is changing very small degrees, we can say, and because of that our oscillator, that or molecule that follows the simple harmonic oscillations and within the parabolic approximation. But real molecules, they may not be following the Hooke's law, because when the, large oscillations are there, in that case there will be change in the bond length, very large amount of change in the bond length, and therefore that bond may not be elastic, and therefore the large molecular vibrations, they are unharmonic. And because of that, the energy levels we are seeing they are having equally spaced. But in the case of such large vibrations, in the case of real molecules, spacing between the adjacent energy levels for high n is less than the spacing between the adjacent level for low n. That means for lower values of n, the separations are much higher compared to the large n values. For large n values, we will get very small spacing between the two energy levels. That means energy levels, they may not be equally spaced in the case of real molecules, right? So this is the vibrational energy levels of a diatomic molecule. So in the today's lecture, we have studied the vibrational energy levels of a diatomic molecule, and we have also studied the vibrational spectrum of the diatomic molecule, right? So we have considered the parabolic approximations. Within that, we considered our molecule is following the simple harmonic oscillations. So it follows the Hooke's law, and by using quantum mechanics, we apply the quantum mechanics laws, and we get the energies of the oscillator, which we are seeing they are quantized, right? So energy levels are quantized, and because of that we get different distinct energy levels, and they are equally spaced, right? So this is the vibrational energy levels of a diatomic molecule. So in the next lecture, we are going to study the problems based on this chapter, right? Thank you.